As satellites have increased in size, the Titan family of launch vehicles has evolved to meet the challenge. Titan IV provides the heaviest space transportation lift capability for the free world. Titan IV, begun in 1985 by the United States Air Force, is capable of placing approximately 25 tons of spacecraft into low Earth orbit. Like all other space launch vehicles, the mission of the Titan IV is to place satellites into one of four basic orbits: low Earth, geosynchronous, planetary, and Marietta. Satellites in low Earth orbit circle the Earth from about 150 to 500 miles altitude. This orbit is used primarily for observation of Earth resources, agriculture, and weather. From the low Earth orbit, satellites can be placed in geosynchronous orbit through an orbit maneuver. This orbit is at 22,300 miles altitude and is almost always in the same plane as the equator. Satellites in geosynchronous orbits rotate at the same speed as the Earth and appear stationary over the Earth. This orbit is used primarily for communication satellites. Planetary orbits, like geosynchronous, begin from a low Earth orbit. Through a transfer orbit maneuver, the satellite is placed on its trajectory to intercept a selected planet. NASA missions to Venus and Mars use this type of orbit. The Marietta orbit is a highly inclined orbit. The high point, or apogee, is about 35,000 miles altitude. The low point, or perigee, is about 300 miles altitude. The Marietta orbit is used most often for communication satellites where coverage of the extreme northern or southern latitudes is required. To place a satellite into the low Earth orbit, the reference trajectory launch sequence begins with ignition of the solid rocket motor, or Stage 0. Stage 1 ignites at 116 seconds, shortly before Stage 0 terminates, separates, and falls away from the core. The payload fairing separates at about 230 seconds. Upon ignition of Stage 2 at about 280 seconds, Stage 1 separates to fall back to Earth. Stage 2 carries the satellite into orbit and then is separated at about 530 seconds. The Titan IV is produced for the United States Air Force Space Division in Los Angeles, California, a division of Air Force Systems Command. It is built by an aerospace team headed by Marietta Corporation, the nation's most experienced contractor of heavy-lift space launch systems. The Titan IV consists of 5 major segments: the core vehicle, solid rocket motors, upper stage, payload fairing, and avionics. The core vehicle, or airframe, is manufactured by Marietta Astronautics Group in Denver, Colorado. The core provides the basic structure and the tanks for the liquid propulsion system. There are 2 separate propulsion systems, Stage 1 and Stage 2. Each stage contains separate fuel and oxidizer tanks. The engines for the liquid propulsion systems are made by Aerojet Tech Systems Company in Sacramento, California. Stage 1 has 2 engines and delivers about 550,000 pounds of thrust. Stage 2 has 1 engine that delivers 105,000 pounds of thrust. The solid rocket motors, or Stage 0, are manufactured by United Technologies Corporation in San Jose, California, and Hercules Corporation in Magna, Utah. The UTC solid rocket motors have a steel case of 7 segments. They are 112 feet long, 10 feet in diameter, and deliver 2.76 million pounds of thrust per launch. The Hercules solid rocket motors have a filament-wound graphite epoxy case of 3 segments. They are 112 1/3 feet long, 10 1/2 feet in diameter, and deliver 3.4 million pounds of thrust per launch. For some missions, there is a third or upper stage. A third stage boosts satellites to the higher altitude orbits. 2 different third stages are available for use on the Titan IV. Originally made for the shuttle, the inertial upper stage is being adapted by Boeing Corporation in Seattle, Washington. It is used for satellites up to 5,300 pounds. The other upper stage is a special Centaur configuration, modified by General Dynamics in San Diego, California. The Centaur is used for satellites up to 11,500 pounds. The satellite is protected by a payload fairing, or shroud, manufactured by McDonnell Douglas in Huntington Beach, California. There is a family of fairings from 56 to 86 feet in length. The size of the satellite determines which fairing is used. The payload bay is 15 feet in diameter and up to 60 feet in length. Its maximum size corresponds directly to the payload bay of a NASA Space Shuttle orbiter. The Titan IV avionics systems command and control the vehicle to place it in the desired low Earth orbit. They also provide communication with the launch site. The inertial guidance system is made by Delco Systems Operations in Santa Barbara, California. The instrumentation system is provided by SCI Technology Incorporated in Huntsville, Alabama. And the command destruct receiver is provided by Cincinnati Electronics Corporation in Cincinnati, Ohio. Two launch complexes are used for Titan IV: Cape Canaveral Air Force Station in Florida and Vandenberg Air Force Base in California. Both launch sites are operated for Titan IV by Martin Marietta. Launches from Cape Canaveral are usually to higher orbits. Launches in the designated area can be made without overflight of habitable landmass upon ascent. Launches from Vandenberg are usually to a low Earth orbit. Launches in this designated area can be made without overflight of habitable landmass upon ascent. The Manaya orbit can be reached from either Cape Canaveral or Vandenberg. Assembling a Titan IV for launch is different between the east and west coasts. At Cape Canaveral, the launch vehicle is built up or assembled on a launch transporter. The core stages and liquid engines arrive by aircraft. At the vertical integration building, the engines are attached to the stages. The stages are erected on the transporter, and the avionics are added. The solid motors arrive in segments by train. After individual segment subassembly and inspection, they are taken to the Solid Motor Assembly Building, or SMAB, where 5 of the 7 segments are stacked. The core is transported from the Vertical Assembly Building to the Solid Motor Assembly Building. There, the assembled 5-segment motors are mated to the core vehicle. The stack is then moved to Launch Complex 41 and placed over the exhaust ducts adjacent to the umbilical tower. The last 2 segments and forward closure of the solid motors are added on the launch pad. The upper stage, if required, is placed on the stack. The satellite and protective fairing are installed. Total vehicle checkout is completed. the propellants are loaded, the mobile service tower is moved back, and the Titan IV is launched. The process is slightly different at Vandenberg Air Force Base. The entire launch vehicle is assembled on Space Launch Complex 4 East. The core components arrive by aircraft and are taken to the Vehicle Assembly Building. There, the engines are installed and avionics are added to each stage. The solid rocket motors arrive by rail. After individual segment subassembly and inspection, they are taken to the launch pad where they are stacked. After electrical checkout, the core stages are taken to the launch pad and mated to the solid rocket motors. The satellite and payload fairing are emplaced. Total vehicle checkout is completed and the propellants are loaded. The tower is moved back and the Titan IV is ready for launch. As to the Titan IV program progress, the liquid rocket engines finished all tests on June 12, 1987 for Stage 2, and July 20, 1987 for Stage 1. The Aerojet general hardware was the first to arrive at Cape Canaveral on December 18, 1987. On January 11, 1988, the first core vehicle was loaded onto a C-5A and flown from Denver to Cape Canaveral Air Force Station.
Isn't that beautiful?
3 days later, Secretary Aldridge presided over the arrival of the Martin Marietta core and Aerojet General liquid rocket engines, as well as the dedication of the Launch Complex 41 at Cape Canaveral Air Force Station, Florida. On February 14th, the second static firing of the UTC solid rocket motors in Coyote Canyon, California was conducted. This was the second and final test of the SRMs. All test parameters have been met, and the new 7-segment SRMs are now certified for flight. The McDonnell Douglas payload fairing completed a critical milestone on March 8th. The 56-foot, 5-ton structure was successfully separated at the Arnold Engineering Development Center, Tullahoma, Tennessee. The significant accomplishments on the SRMUs include 3 of 4 quarter-scale burst tests have been completed, with all exceeding expectations. The nozzle flex seal shim has been successfully molded to Titan IV thickness. And finally, Hercules has started winding the first full-scale test articles on July 17th. The structural test at Denver on Stage 1 and Stage 2 are continuing in the vertical test facility. A variety of load conditions simulate stresses exerted by flight conditions, as well as verifying that the structure will sustain loads 25% higher than flight conditions. These tests verify the structural integrity of the hardware. Strain gauges are used to measure deformation, indicating stress and thus load in the structure. Deflection gauges measure actual movement of critical locations on the stage and are used to verify stiffness characteristics. Results of the stiffness measurements are compared to forecasted results from design models. Computer-aided analysis then verifies the capability of the Titan IV hardware to perform its mission. The Titan IV Centaur progress includes refurbishment of the structural test tower and construction of umbilical test tower at Sycamore Test Facility. The major weld of the structural test tank was started. Hardware arrival and processing at the Cape for first launch continues. The core Stage 1 and Stage 2 have had the engines installed and were stacked. The solid rocket motors completed non-destructive testing and were transported to the solid rocket motor assembly building. The payload fairing arrived by air and was processed through the PLF processing annex. On May 16th, the core vehicle with engines and avionics in place and checked out was moved from the vertical integration building to the solid motor assembly building. The twin locomotives shown here move the 116-foot stack on the launch platform at 4 miles per hour. At the solid motor assembly building, the solid rocket motors were integrated to the core. Integration and checkout took place May 16th through 19th. On May 21st, the twin locomotives transported the 116-foot tall stack on its 45-minute journey to the umbilical tower, or UT. At the UT, the final 2 segments of the solid rocket motor were attached along with the forward closure. The inertial upper stage was processed through the east bay of the solid motor assembly building and transported to Launch Complex 41, where it was removed from the transporting container. On June 16th, the IUS was placed on the stack. As a part of finishing the last developmental tests, the mobile service tower was rolled back, and the Titan IV, complete with the PLF, was seen for the first time. Work on Flight 2 is well underway. The core Stage 1 and Stage 2 were shipped to Cape Canaveral on July 14th. The liquid rocket engines have arrived. The SRM segments have begun processing. With the Titan IV, the Air Force will be buying launch services instead of launchers as in the past. They will rely on Martin Marietta's program management and delivery schedules to meet the national spacecraft need. Manifesting is guided by the Space Division. Martin Marietta is building the required vehicle inventory to provide for the flexible response to meet the nation's changing needs.